All right, good morning, everybody. So the topic of today's lecture is something called Liskov Substitutability. So the Liskov substitution principle is named after Dr. Barbara Liskov. If you click that link, it'll take you to her Wikipedia webpage. So the principle is named after her and Jeanette Wing. They're both professors of computer science still, which is kind of surprising. She's over 80 right now. Anyway, they're still practicing computer scientists. Amongst Dr. Liskov's many accomplishments, she is a Turing Award winner, so that's the highest prize in computing science. And she invented this language called, well, her and her students invented this language called CLU. Now, why am I telling you about this? Because CLU, which was developed in the 1970s, was the language that popularized or actually invented many of the features that you use today. So for example, abstract data types, CLU. Right? Iterators, CLU. Multiple return types. So in Python, when you return a tuple, that idea came from here. Type-safe parameterized values, so that's generics. That's what we're going to start talking about in the next lecture. All came from CLU. So that was it was an early object-oriented programming language, so it had classes and constructors. And also, it popularized the idea of exception handling. So that's like five or six of the main features of the Java language. They all came from this language called CLU, or one of the predecessor languages to CLU. Okay, so there is a formal, i.e. a mathematical definition of what the Liskov substitution principle says. You don't need to know the mathematical definition. What you need to know is the following. A subclass object must behave the same as objects of their supertype. Right? So in other words, subclass objects should always be substitutable for their supertypes. Now, the problem with this is that the language can't help you ensure that this is the case. Right? So in other words, so Java provides you with the ability to implement an inheritance hierarchy. It also gives you the ability to completely implement it incorrectly. And there's nothing you can do about that. So I don't think there's any object-oriented programming language that actually formally tests if subclass objects are correctly substitutable for their superclass types. So this means that the programmer, all this responsibility falls onto the programmer. So the programmer has to pay careful attention when they're implementing their subclass types. If you ensure Liskov substitutability, then that allows a programmer or other programmers to write code where they only look at the superclass contracts. And any code that they write should work with every subclass type. Right? So in other words, someone can write a method that uses the class object, and you should be able to pass in any reference to that method, and that method should work the way it's expected to. Right. Okay, so now remember that classes have these things called invariants, right? Methods and constructors have these things called preconditions and postconditions. Right? So substitutability affects all of these. Well, substitutability interacts with all of these things. So if a class has some class, if a superclass has some class invariants, right, then that means that the subclasses inherit those invariants. And what does that mean? It means the subclasses have to also obey those invariants. Right? So the reason this happens is because invariants are public features of a class. Right? So anybody using the class can see that this is true. Right? Normally, you actually tell people what the invariants are, which means the invariants are inherited by its descendant classes. If a subclass fails to support the invariants of its ancestor classes, that can cause code that's correctly written to break. So that's the important part here. Right? So these 2 points here. Right? Number one, someone can look at the superclass contracts and say, I'm going to write my code using these contracts. Right? If they write their code correctly, then they should expect their code to be able to work regardless of the subtype object, the subclass object that's passed into their methods. Right? Now, if you mess up your inheritance hierarchy, so in other words, if you implement a subclass and you do something incorrect, right, then that causes other people's code, or can cause other people's code that seems to be correct to break. Right? And you don't want that to happen. All right, so the counter class is an example of a very simple class that has a class invariant. right? It promises that the value of the counter is never negative, right? Now, what does that mean? So someone sees the counter class, they say, hey, the counter value is never negative. I can write some method that relies on this fact, right? So for example, someone can write is odd, right? They want to know, is the value of the counter odd or not, right? So this returns true. If the value of the counter C is odd, it returns false if it's even. Right? Now, how can you implement is odd? In this case, you can write, right, return C value, take the remainder after dividing by 2, and check if it's equal to 1. Right? Now, that's actually not the way you should write this method, right? Because if that value is negative, then the answer is actually -1. Right? In Java, the sign of the value that's returned by the remainder operator gets, is that true in Java? Is it always the sign of the first argument? I don't remember how it works exactly now. Anyway, if this is negative, then the answer is -1, and this fails. Right? So this method fails to detect odd numbers that are negative. Right? The correct way to write, or the quote unquote, the better way to write this is to write not equal to 0. Right? Because if you divide by 2 and it's even, regardless of it's positive or negative, the answer is 0. Right? So someone can write this code, right? They've looked at the contracts for counter and they've seen, hey, counter says it's never negative, so this code is fine. You can write every possible unit test, right? In other words, you can make a counter with every possible value. Send it to this method, and this method will always return the right result, always return the correct result. Right? So this method is quote unquote provably correct for all counters. Right? And now someone can come along and break this method, right? Without even touching this code. Right? So someone can come along and say, hey, I've got this count, I need to count something, but I need to count down. Right? I've got this counter class, so I'm going to subclass it, and I'm going to make something called a descending counter. Right? So a descending counter simply counts down. Right? Every time you advance the counter, it goes down by 1. Right? Now that breaks the abstraction of our counter. Right? Our counter says it always counts up, but never mind, we'll count down. Right? Furthermore, their counter counts down past 0 towards negative min value, towards integer min value, right? A negative value. When it hits integer min value, it wraps back around to integer max value. So this is super easy to implement, right? You just subclass counter, right? Throw in your constructors, right? What do you do in your constructor? You always call the superclass constructor on the first line, right? So everything's correct here. No field to store the value because that field lives in the counter class, right? Override advance. What does advance do? It just subtracts 1 from the value, right? And you're done. So a few lines of code, you've got a functioning descending counter. What's the problem, right? You take this descending counter and you pass it to that is odd method, right? If the value of the descending counter is negative, is odd suddenly fails, right? So in other words, by creating a subclass, you've broken someone else's code, which shouldn't happen. Okay, so if a subclass inherits some invariants, it has to make sure that the invariants are true in the subclass as well. Right, now does that mean that the subclass has to make sure it has the exact same invariants? The answer is no. Right, so a subclass can modify its inherited invariants as long as the modification still satisfies the ones that it inherited. Right, so for example, our counter says that the value of the counter is always non-negative, right? But it doesn't say anything else about the value, right? It simply says it's not negative. So you can come along and make a ranged counter that counts between 2 non-negative values, right? So say between 5 and 10, right? That's different than how a counter works, right? Counter counts between 0 and integer max value, right? So we've changed the invariant, right? But the invariant still satisfies the original invariant from the counter class. Right? So again, it's easy to implement this class, right? You make a class, you extend counter. Now in this case, this is an example of a subclass where you need to add your own fields, right? Because this subclass needs to know, so objects of type range counter need to know what their minimum value is, and they need to know what their maximum value is. Right? So now you're going to add a pair of fields for the min and max value of the counter. Right? Your invariant is different than the counter class, right? The minimum value is greater than or equal to 0. The maximum value is greater than or equal to the minimum value. So we change the invariant, but we've changed it in such a way that the superclass contracts are still respected, right? So in other words, we still satisfy the superclass invariant that the value of the counter never be negative. Right? So it's possible to change the invariants. You just have to do so in a way so that your subclasses are still substitutable for their ancestor classes. All right, any questions about that? So that's how invariants interact with inheritance, right, and substitutability. Right, now notice the language doesn't help you here, right? So you can make this descending counter, and there's no way for Java or the compiler or anything to check whether or not this thing is really substitutable for the counter class. Right, so all the responsibility of ensuring substitutability, it lies on the programmer. All right, so I'm going to switch gears now and talk about this thing called the shape class. This is in the notebooks if you've been reading the notebooks. The shape class is an example of what's called an abstract class. Right? So it's meant to represent, so it's a simple class that's meant to represent 2D shapes, right? So squares and rectangles, triangles, circles, things like that. Now, we haven't seen abstract classes yet. So what's an abstract class? Well, I guess we can start by saying what an abstract class can't do, right? So an abstract class is a class where you don't use it to make objects directly. Right? So what does that mean? So shape is abstract. So what that means is you can't write something like shape equals new shape S equals new shape. Right? So in other words, you never directly make a shape object. So if you never directly make a shape object, what's the purpose of the class? Well, the purpose of the class is to serve as a building block for other classes. Right? So in other words, the only purpose of an abstract class is to act as a superclass in an inheritance hierarchy. Right? Now, why might you want to do this? So if you have an abstract class at the top of your inheritance hierarchy, right, all the methods, all the non-private methods, I guess all of the public and protected methods of that class, right, those methods define what all shapes can do. Right? So in other words, you declare all of the methods that you want to be common for all 2D shapes. Right? And now what else can you put in there? Well, an abstract class is just a class, so you can put in fields as well. Right? Now what does that mean? If you make the fields protected or public, not public, normally protected, right, then all of your subclasses also inherit those fields. Right? So in other words, it declares all of the fields that are common to all 2D shapes. Right? So in other words, someone subclasses shape, and they get all of the methods and all of the fields that are defined in the shape class. Right? It acts as a building block for other classes. When you draw the UML diagram, the UML class diagram for an abstract class, it looks exactly the same as a regular class, except that the name of the class is written in italics. Right? So it's a very subtle distinction on a UML class diagram. So shape is going to be the class that sits at the top of our shape hierarchy. Right? Okay, so our class is abstract, so it should have some methods, and it should have some fields. Right? So here's our abstract class called shape. To make a class abstract, you just use the keyword abstract in front of class. Right? And that automatically makes the class abstract. If you try to make a shape object by writing new shape, the compiler will complain. All right, our superclass has some invariants up here. So it has a description and some invariants up here. Right? So the description for the shape class says it's the superclass for 2D shapes that have an independent width and height. Right? So in other words, every shape you can change its width and height independently. Furthermore, the width and height are always between 1 and 100. Right? So we have an invariant there as well. If every shape has a width and height, then it makes sense to make those fields of the abstract class. Right? So that way anybody who inherits from the shape class automatically gets the fields width and height. Right? We make them protected so that the subclasses can access them directly by name. We have two public static final constants that represent values that are important to the shape class, right? So we have the min length and max length, so that tells everybody what the minimum and maximum length of a shape is, right? And then you've got some constructors, right? So even though you don't make shape objects directly, the shape class still has constructors, right? So who's going to call the shape constructors? It's going to be the subclasses that call the shape constructors, right? So on the first line of any class such as rectangle or square, right, you're going to call the shape constructor by writing super blah, right, super something, right? So the shape class still has constructors. Its constructors still set the width and height of the shape object. Okay, so methods can have post conditions, right? So in other words, methods can promise something about the value that they return. The width method promises to return the width of the shape, and it promises that the value returned is always between 1 and 100. Right? That makes sense because that's also the invariant of the class. Right? So width makes a promise about its return value. Okay, so keep that in mind. Area upper bound. So here's another method. This method promises to return something. Right? It promises to return an estimate of the area of a shape. Right? Now, why an estimate? Because you can have a complex shape. Right? You can have if you draw some smooth, curved, two-dimensional shape, it's very hard to calculate the area of that shape exactly. Right. So area upper bound promises to return an estimate of the area of the shape. Furthermore, it promises that the estimate is always greater than the true area of the shape. Right? So if you've got, for example, so if you have a circle of radius r, area upper bound in this case would return r squared. Sorry, it would return 4r squared. Right? So the method in the shape class just returns the width times the height of the shape. Right? Furthermore, it says some other stuff. It says if the subclass knows how to compute its area more accurately, then it should do so. And then one more, we've got a method called set dimensions. Now, set dimensions is a method that has some preconditions. Right? So remember what a precondition is. A precondition is some condition that has to be true when the caller calls the method. So set dimensions promises to change the width and height of the shape to the specified width and height. Right? So you call set dimensions with 4, 5, and then the size of the shape should change so that its width is 4 and its height is 5. Right? The class has some invariants, so these parameters have some conditions on them. Right? The value of the width and the value of the height have to be between 1 and 100. So here's an example of a method that has some preconditions. Right? Now remember, the preconditions are going to interact with substitutability. Okay, so using the shape class, someone can write a method. So all we're going to do is we're going to look at these contracts, right? So we're going to look at the set dimensions contract. We're going to look at the area upper bound contract. We're going to look at the width contract, and we're going to we're going to keep in mind that our class has some invariants. We're now going to use the class, right? So I'm going to use shape to write some methods that work on shapes. Right? Furthermore, any method that I write using the shape contracts should work for any shape that you try to pass into the method. So I can write this method called random scale. Right? So random scale is going to try to randomly change the size of a shape. Right? So what it actually does is it scales the shape's width and height by some random value between plus and minus 0.5% of the current width or the current height. Right, so that's all that this equation is doing here. Right, this is just 1 plus math random returns a value between 0 and 1. Right, that's 1%. Right, that's 0.5%. So that's up to 1% minus 0.5%. Right, so in other words, between minus 0.5% and plus 0.5%. Right, multiply that by the width, and that changes the width slightly. Right, you do the same thing for the height. Right, again, 1 plus the value between 0 and 1% minus 0.5%. Right, so in other words, change its size plus or minus 0.5% of its height. Right, so that's our new width and new height. Now we actually do the correct thing. We check if the new height and the new width are between 1 and 100. And if they are, we go ahead and change the dimensions of the shape. Right? If not, we do nothing. So in other words, it doesn't change the size of the shape. And that's fine, right? So based on the contracts of set dimension, and I guess width and height. Well, set dimensions. I guess just based on the contracts for set dimensions, right? This method is always correct, right? It will always either change the size of the shape or not, right? And it'll never throw an exception, right? So this should work for any shape that you pass into it. Okay, so now what happens if we decide to extend shape, right? So now I want to make some subclasses, and I want to try to break some of these methods that I've written using the shape contracts. So we're going to make a class called rectangle, right? And then from rectangle, we're going to subclass it to make a class called square, right? Now this should be ringing some warning bells, because this is exactly the same as the ellipse and circle problem that we looked at in a few lectures ago, right? So this is saying a square is a rectangle, right? And before we had circle is an ellipse, right? So it's the exact same problem that we're going to run into when we implement the square class. Okay, so that method called set dimensions, it's got restrictions on its parameters, right? So set dimensions requires that the width and height be between 1 and 100. You can write a class that overrides set dimensions, right? So I can make a subclass, override set dimensions, right? Now when you do that, right, you have to make sure that the overridden version of the method also accepts values between 1 and 100. Right? Because that's what the superclass method says it does. Right? The superclass method says, hey, any value between 1 and 100, I will change the width and height to those specified values. Right? Which means the subclasses have to do the same thing. Right? So if a subclass says you can only use the value 50 for the width, that's a problem. Right? Because as soon as someone writes a method like, what I call it, random scale? Yeah, so as soon as someone makes a method like random scale, suddenly their method fails. Right? Because the size is probably not going to be 50. So when a subclass overrides a method, it must accept all of the parameter values that are accepted by its ancestor classes. Furthermore, whatever the inherited version of the method says it does, the subclass version has to do the same thing. Right? So what's the problem with square? The problem with square is that the width and height of a square must be equal, otherwise it's not a square. So if someone implements the square class, right, so that it extends rectangle, they can create a set dimensions method that imposes an extra constraint on the width and height. Right? So notice that this constraint here, where the width must be equal to the height, does not exist in the shape class contract for set dimensions. Right? So what this version of the method is saying is that you can call this method as long as the width and height are equal. Right? Whereas the superclass method says you can call this method with any value of width and height as long as they are in the range 1 to 100. Right? So now that you've added an extra constraint, you've got a problem, or somebody else has a problem. Right? The square class can do this if they want to. Right? The problem is now that squares are not substitutable for shapes. The rest of the class, there's no fields. Right? All of our fields are inherited from the shape class. There doesn't seem to be any extra field that you need to describe a square, so there are no fields here. The constructor for square does the right thing. Right? On the first line, it calls the superclass constructor. Even overriding the method, technically, right, so in terms of the mechanics of overriding, everything's fine. Right? The name is the same, the return type is the same, the parameters are the same. There's an unusual line here that we haven't seen before. Right? So we've got this keyword super that appears a second time now. Right? So in the constructor, on the first line of a constructor, super means call the superclass constructor. Inside of an overridden method, super means call this method that's in the superclass. Right? So call the superclass version of set dimensions. Right? Notice that we're in the square version of set dimensions. Right? Often, when you're overriding a method, you want to call the superclass version of the method, because the superclass version of the method already does something for you. Right? So here, the superclass version of set dimensions actually changes the width and height. So I can just go ahead and call the superclass version of the method. When you want to do this, use the keyword super to indicate that you're calling the superclass version of the method. So this line here ends up calling the rectangle version of set dimensions. The problem with the square class is that random scale pretty much is guaranteed to fail when you pass it a square object, right? It's going to fail because the width and height that random scale chooses are random, right? With near certainty, they're not going to be the same value. When you call set dimensions on the square object, right, the width and height won't be equal, so we'll end up throwing an exception. So our random scale method, which never used to throw an exception, now suddenly throws an exception when you pass it a square object. Right? So remember, when you pass it a square object, when we call set dimensions, right, it's the runtime type of S that determines which version of set dimensions gets called. Right? So if we pass it a square object, the runtime type of S is square. So it's the square version of set dimensions that gets called. And the square version does not accept the width and height that are different. So what have you done? You've managed to subclass a class, and you've broken someone else's code. Right? That's what you just managed to do. Okay, any questions about that? So that's an example of what happens when you override a method and you impose extra constraints on the values that the method accepts. Okay, so this slide here simply describes what the keyword super is used for. Right, so when you're overriding a method, often you want to call the superclass version of the method that you're overriding. Right? If you want to do that, use the keyword super. Right? If you're calling a different method in the superclass, you can just use the keyword this. You can normally use the keyword this. I guess it depends if the other one's overridden or not. All right, so we just saw that you cannot add extra constraints, right, when on an inherited method, but you are allowed to change the constraints. Right? So, for example, I can remove the constraints that set dimensions imposes. Right? So remember, the shape version of set dimensions says the value must be between 1 and 100. Otherwise, we throw an exception. Right? I can remove that constraint that the value has to be between 1 and 100, and I can do something else. So we can remove or weaken any constraints on the parameter values. So if I implement this rectangle class, right, I can implement set dimensions for the rectangle so that out of range values don't throw an exception. Instead, we quote unquote fix the out of range values. Right, so in the rectangle class, right, we can override set dimensions, and we can say that a width or height that is out of range gets clamped to shape min length and shape max length. Right? So in other words, if a length is less than 1, we just set the length to 1. Right? If it's greater than 100, we just set it to 100. Right? So this version of set dimensions will now accept a wider range of values than the superclass version. Right? I can pass in any width and I can pass in any height. Right? So this version of the method actually will accept more values as inputs than the superclass version. That's okay. Right? As long as whatever this method does still satisfies the contracts for the superclass. Right? So all this method does is it just checks, it just looks at the width and height, right? And then it takes the maximum value of the width and min length. Right? So in other words, if width is less than min length, it just sets width to min length. Right? It does the same thing to height. And then it sets width to the minimum of width and max length. Right? So in other words, if width is greater than max length, it sets the width to max length. Right? And then does the same thing for the height, and then it sets the width and height. Right? So this method is fine. Right? It does not break. It does not break that random scale method here. Right? That was written using the contracts for the shape version of set dimensions. Okay, so what about, so that's preconditions. Now what about postconditions? Right? So a superclass method can promise something about its return value, right? So that's documented as normally in the return tag of the Java doc. If a subclass method overrides overrides the superclass method, then the subclass, whatever it returns, it has to satisfy the promise that the superclass made. Right? So what does the width method from shape promise to do? It promises to return the width of the shape. Right? Furthermore, it promises the value will always be between 1 and 100. Right? So if you override width, you have to make sure that it returns the width of the shape. Furthermore, it has to return a value that's between 1 and 100. Right? Now, given that contract for width and height, which I didn't show you, right? So given the contracts for those methods, someone can write a method using the shape contracts. Right? So for example, if I want to write a method that that scales the size of a shape uniformly, right? So it scales it up or down so that the width of the shape is exactly 1, right? We can do that. It's pretty easy to do. Methods like this that set something to 1, right? Like for example, you scale the size of a shape so that its area is 1, or you scale the size of a shape so that its height is 1. Right? We say that those methods normalize the width, height, shape, the width, height, area, whatever it is you're trying to, whatever it is you're changing, right? It normalizes that aspect of the shape. You can do this as long, so how's this going to work? Right? You're going to take your shape, you're going to look at the width, you're going to divide the width and the height by the width. Right? So that sets the width to 1, and it scales the height accordingly. Right? Now you can do this as long as the width of the shape is not 0. Right? Because if you divide by 0, you've got a problem. Right? Furthermore, the height has to be greater than the width, right? Greater than or equal to the width. Otherwise, you end up setting the height to a value less than 1. Right? You can write this method, and it's guaranteed to pass every possible unit test that you can write using the shape contracts. Right? So as long as the width is height is greater than the width, right, I can compute the new height just by taking the current height and dividing by the current width. Right? I can compute the new width by taking the current width and dividing by the current width, which is just 1. And then I can call set dimensions. Right? If this precondition is true, this method should always work. Right? Because we know from the width method, right, that the width method never returns a value that's less than 1. Right? We know from set dimensions will accept any value that's between 1 and 100. Right? From height, we know that the height is never greater than 100. So the new height and the new width are guaranteed to be between 1 and 100, as long as the shape contracts are respected. Okay, so someone comes along and says, hey, I need a vertical line in my shape hierarchy, right? So a line that's straight up and down, right? Vertical lines, so it's a vertical line, so it has no width, right? So its width is 0. Right? There's nothing from stopping a programmer from implementing such a class, right? It's bad it's bad when you consider substitutability, right? Because it breaks, number one, it breaks a class invariant, right? Shape class says the width or the dimensions of the shape shall not be less than 1. Right? Furthermore, when you override the width method, width is going to return 0 because it has to return the width of the shape. Right? And that's not a value between 1 and 100. It's easy to implement this class. Right? It's like 5 lines of code. Right? So make your vertical line class. It extends shape. Call the superclass constructor on the first line of your constructor. Set the width to 0 because that's the width of a vertical line. What does the width method return? Well, it returns 0, right? And that's a problem, right? The return value is not between 1 and 100 here. That's a problem because you've broken one of the class invariants that you inherited from shape. Right? Now, what's the problem if you return a width of 0? Right? When you divide by 0 here, that ends up being positive infinity. Right? When you call set dimensions with a height of positive infinity, you end up with an exception. Right? So code that was provably correct is no longer correct. Right? So the normalized width method now fails when you pass it a vertical line object. Right? In other words, you broke someone else's code by creating a subclass. And again, there's no way for the compiler to help you here. Right? There's no way for the compiler to look at this code and say, hey, this is not, this breaks some contract from the superclass. Right? Because the compiler can't read your English documentation or your written documentation and infer that this is a problem. Right? Okay, so that's what happens with a return value. All right? So that's what happens when the return value is not compatible with the superclass description of the method. Now, does that mean that a subclass always has to return the exact same value as the superclass method? The answer is no. Right? It can return any value as long as the superclass contract is still respected. Right? So the triangle class can override area upper bound, right? And it can actually return the true area of the triangle, right? So in other words, it doesn't have to return an upper bound on the area. It can return the exact area, right? And it's easy to do because the area of a triangle is just 1/2 the width times its height, right? So to implement the triangle class, right? No fields because the width and height, those fields belong to the shape class, right? In your constructor, call the superclass constructor, override area upper bound, and return the true area of the triangle, right? Notice that the contract of area upper bound actually changes, right? So now the contract says it's going to return the true area of the triangle. If you go back and look at the area upper bound contract in the superclass, it's much longer, right? It goes on and on about returning this upper bound, blah, 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 right? Now it's just, well, I'm going to return the true area, right? This is fine. It satisfies the contracts of the superclass. Okay, now what about mutator methods? So mutator methods are methods that change the state of an object, right? Set dimensions changes the width and height of a shape, so it's a mutator method. If you have a superclass mutator method, then the subclass version of that method has to ensure that the state of the object is changed in a way that satisfies the promise of the superclass. Right? So in other words, the superclass version, the overridden version of the method has to promise something that's similar to the superclass version. Right? So back to set dimensions and square. Right? If someone really wants to try to force square to be a shape, right, then they can try to fix up their set dimensions method. Right? So remember before set dimensions, the square version of set dimensions checked if the width and height are the same, and if they're not, it throws an exception. Right? We know that's a problem. So you might try to fix the square version of the method some other way. Right? So for example, you might ignore the height. Right? So this version of set dimensions takes in the width and height. Right? It doesn't impose any extra restrictions. Right? So whatever value of width and height this method, the superclass version accepts, this one also accepts. Right? But what does it do? It now completely ignores the height. Right? So in other words, it sets the size of the square to be the height of the width of the square to be equal to the width, right? That value there. And it sets the height of the square to be also equal to the width. Right? So in other words, we simply ignore the height parameter. Now what's the problem with this? Right? The superclass version of the method says, right, this method shall set the width and height to the specified width and height. Right? This one doesn't. Right? It sets the width to width and it sets the height to width. Right? So you can easily cook up a method, right, written using the shape contract that now suddenly fails when you pass it a square object. Right? It's easy to do. Right? You just write a method that depends on the height changing. Right? Now when you pass it a square, the height doesn't change to the expected value. Okay, so so imagine that you're talking to your colleague who's trying to write this square class, right? And you say, hey, this is a problem, you got to do something else about this. Right? So your colleague says, fine, I'll fix this some other way. Right? So instead of ignoring the height, we'll ignore both of them. Right? So we're going to ignore the width and the height and do nothing. So set dimension suddenly does nothing. Right? Instead, whoever implements square says, hey, look, if you want to change the size of a square, call set length instead. Right? So I'm going to introduce a new method set length. You're allowed to do that in a subclass. Right? There's no restrictions on this method. Right? As long as, sorry, that's not true. There's no inherited restrictions on this method except for whatever the class invariants say. Right? So introduce a new method, now you can put whatever restrictions you want. Right? and it can do whatever you want. So now you get to write the contract for set length. So set length just takes in the length, and it sets the width and height to that value. Right? So now they're telling you, hey, look, you can't call set dimensions anymore because set dimensions does nothing. Right? Instead, call set length. This actually introduces two problems. Right? Problem number one is that set dimensions now does not satisfy its inherited contract. Right? It does not change the width or height. So again, it's easy to make up a method that uses the shape contracts, and now suddenly, when passed to square, it breaks, right? Because it doesn't actually change the width or height of the shape. Right? Problem number two. Problem number two. Right? Whoever's using this square class can no longer use it polymorphically when they want to change its size. Right? So the whole point in putting in a set dimensions method in the shape class is that someone can always call set dimensions, and the size of the shape should change. Right? Now, if they're working with a square, they have to call a different method. Right? So in their code, what ends up happening is they end up writing code that looks like, if the shape is an instance of a square, right, call set length instead of calling set dimensions. Right? And now now all of your code ends up with a bunch of these ugly if statements that check the actual runtime type of a shape. Right? And that's what you want to avoid doing in a well-designed inheritance hierarchy. Right? So is there any way to fix set dimensions for the square class? The answer is no. Right? Why is the answer no? Because if you go all the way back to the contract for the description of the shape class, right, it says it's the superclass for shapes that have independent width and height. Right? Squares and circles can't have independent widths and heights. Right? So you cannot implement squares and circles under this hierarchy and have substitutability work all the time. Right? So the only solution here is to go back and change the description of the shape class. Right? So you have to strike this independent width and height. Right? If you do this, you have to modify the contracts for things like set dimensions. Right? So when you modify set dimensions, the contract for set dimensions, you have to say something about certain subclasses might not let you change the width and height independently. Right? But as it stands, there's no way to correctly implement square or circle in this hierarchy. All right, so what did we talk about today? We talked about Liskov substitutability. Right? What do you have to keep in mind when you're implementing an inheritance hierarchy and you want to make sure that your subclasses are substitutable for their parent classes? Right? You have to pay attention to the class invariance. Right? You have to pay attention to any method that has a precondition on its inputs. Right? And you have to pay attention to all of the postconditions of your methods. Right? So whatever a method promises to return in the superclass, you have to return a compatible value when you override the method. Right? If a method says that it's going to change the state of an object, right, then when you override the method, you have to change the state of the object in a compatible way. Right? No way for the compiler to help you with this stuff. It's the responsibility of the programmer to make sure that subclasses really are substitutable for their parent classes. Right? If all of this seems difficult to, or it seems complicated to understand, it turns out it is. Right? So in many real-life inheritance hierarchies, especially in older code, substitutability isn't really guaranteed. Right? So in other words, it's not that uncommon to see subclasses that are not really substitutable for their superclasses. I think we've gotten better at this since in more recent times. Certainly when object-oriented programming languages were newer or started being used more widely, there was a lot of problem with creating inheritance hierarchies. Okay, I guess the last thing I want to talk about is, so someone asked a question in another class. They asked, so what's the difference between an abstract class and an interface? Right, so remember, shape is abstract. Where's shape? Okay, shape's abstract, right? So in other words, what does shape do? It defines what methods all shapes have. Right? It also defines what fields all shapes have. Right? Now, what would a shape interface have? Well, a shape interface would also define what all methods shapes have. right? But in an interface, you can't have any fields, right? So one of the differences between abstract classes versus interfaces is that an abstract class can have fields, right? If you want all of your subclasses to have certain fields, you should use an abstract class instead of an interface. If you want all of your subclasses only to have certain methods, then you should prefer using an interface as opposed to an abstract class. All right, any questions? Okay, I guess that's it. I don't have any announcements for you. I'll see you in a couple of days.